Welcome to RSIT Online. I am Rita from the Department of Electrical and Electronics, Rajagiri School of Engineering and Technology. The topic of my lecture for today is on synchronous counters, and this is the first part of the lecture. In this lecture, we deal with what are synchronous counters, the difference between asynchronous and synchronous counters, and the steps that we consider for designing synchronous counters. So first we'll see in general what synchronous counters are. Synchronous refers to events that have a fixed time relationship with each other. Synchronous counters, as we have shown in the figure, we can see that for both the flip-flop, we have given the same clock signal at the same time. If we look at the figure, we can see there are two flip-flops, and for both the flip-flop, the same clock signal is provided to both of them. If you remember about the asynchronous counters, in asynchronous counters, we have seen that the reference clock is provided to the first flip-flop, and the output of the first flip-flop is given as the clock for the next one. So the major difference between a synchronous counter and an asynchronous counter is that in synchronous counters, the clock is given to all the flip-flops at the same time, while for asynchronous counters, the clock is given to the first flip-flop and the output of the first flip-flop is given as the clock for the second. Also, one major difference we can see between both the synchronous counters and the asynchronous counter is that in synchronous counter, the clock frequency to both the flip-flops is having the same frequency. While if you look at asynchronous counter, the frequency that is coming for the second flip-flop is different from that of the first flip-flop. So that is also one of the major differences in asynchronous and synchronous counters. Here we brief on the differences between synchronous and asynchronous counter. As we had seen before, if we look at both the counters, that is in synchronous and in asynchronous, construction-wise, the asynchronous counter is simpler because the output of the first flip-flop is given as the clock for the second. While for synchronous, the clock is given simultaneously to all the others, and the inputs that are given depend on different logic circuits, which we'll see in detail in the design part. If we look at the propagation time, we can see that for asynchronous, since the clock is provided to one flip-flop and the output is taken as the clock for the second one, the time it acts is like a ripple action. That is, the first flip-flop works and then the second flip-flop works. So there is a propagation delay which is equal to the number of flip-flops into the delay of one flip-flop. While in synchronous counter, we can see that since the clock is given simultaneously to both the flip-flop, it acts at the same time, and therefore there is lesser propagation delay. As mentioned before, the clock provided is same for both the flip-flops in synchronous, while in asynchronous it is not the same. Then for asynchronous, the operating frequency, as we have seen, it changes, while for synchronous, the operating frequency is higher. Now the speed of operation for asynchronous, since it is one flip-flop after the other, it is lower, while in synchronous, it is faster since the clock is provided to all the flip-flops at the same time. The components required for asynchronous lesser, while in synchronous it is more. Because of that, we can see the cost will be lesser for asynchronous and more for the synchronous. A major disadvantage of asynchronous counter is the presence of glitches, and these glitches are caused because of the higher propagation delay. While there is a lockout condition in synchronous counters, which we will see in detail in this lecture. So now we have briefed on the difference between asynchronous and synchronous. We'll go into the details of designing a synchronous counter. These are in general the steps carried out for designing a synchronous counter. First step is we have to determine the number of flip-flops that is required to design the counting sequence. Now how will we decide on the number of flip-flops? So the number of flip-flops we can obtain from the relation that 2 raised to n minus 1, where the small n represents the number of flip-flops that is required. 2n raised to n minus 1 should be greater than or equal to the highest number in the counting sequence. That is, if in the counting sequence the highest number that we have to achieve is 7, then we require 2 raised to 3, and the number of flip-flops is 3. So 2 raised to 3, which is 8 minus 1, gives you 7. So after we decide on the number of flip-flops that is required, we have to determine the type of flip-flop that we require for designing our counter. So we know that there are different types of flip-flops, that is SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. These are the different types of flip-flop that we have studied. So either one of these flip-flop can be chosen for designing our counter. Next, we must be familiar with the excitation table of our flip-flop. With respect to that, we can develop the state transition diagram, the state excitation table, and we simplify the expression to obtain our flip-flop implementation using K-map. We will see all these in detail in the following slides. So with an example, we will start. Suppose we want to design a 2-bit synchronous counter or mode 4 counter. Now with 2 bits, we know we can count up to 0 to 3. That is 0, 0, 0, 1, 1, 0 and 1, 1. Since there are 4 different states, that is 0, 1, 2, 3 and 3, we call it a mode 4 because we have 4 different modes in our counting. So since we have to count 4 different modes and the highest number we are going to count over here is 3, the number of flip-flops we can obtain as 2 because if we remember, if we go back, we can see that the number of required flip-flop is 2 raised to n minus 1 and the highest number we are going to count over here is 3. So in order to get 3, n should be 2, that is 2 raised to 2 minus 1, so that is 3. So the number of flip-flops we are going to use is 2, and for this example, the type of flip-flop we are going to take is JK. So according to the steps we know, once we fix on the type of flip-flop, we have to obtain the excitation table. Now what do you mean by excitation table? So excitation table is when you have the previous value of your output, we need the next value. To obtain this next value, what are the inputs that we can provide to the JK? So to get a better idea, we can look into the truth table of JK flip-flop. So for JK flip-flop, we know that when J and K are 0 and 0, the output holds on to the previous value, that there is no change. When J is 1 and K is 0, our output sets to 1. When J is 0 and when K is 1, our output sets to 0. And when J is 1 and K is 1, we know it is known as the toggle state. That is where the output is toggled to it. If it is 0, it becomes 1, and if it is 1, it becomes 0. So for the first case of our excitation table, we have seen that the previous value is 0 and the next value is 0. So here we can see that we are holding on to the previous value. So when we are holding on to the previous value, we know the condition is for J and K is 0, 0. So one case when we are holding on to the previous value, we have J 0 and K 0. Next we have seen for the case when J is 0 and K is 1, our output is 0. So we can obtain the next value as 0 when J is 0 and K is 1. So from this we can see that our J must be 0 and our K can either be 0 or 1, which means that we don't care what the value of K is. So that is why we put it as a don't care. Similarly, we can take the next case. When our previous value is 0 and our next value is 1. So here we can see that there is a toggling effect. That is, the 0 has become 1. So for the toggle effect, we know j is 1 and k is 1. So we have 1 and 1. And to obtain our output as 1, we know the case is j is 1 and k is 0. So you can write another k is 1 and 0, which shows that our j must be 1 and our k can have either value of 1 and 0, which means that k can have any value and we don't care about the value of k. So that is how we write over here, it is as 1 and don't care. Similar method is used for the other two rows when the previous is 1 and the next is 0. When the previous is 1 and next is 0, we know that we are toggling. So one effect is 1 and 1 and the other case is you are going to get a 0, which means our k must be 1 and we don't care about the value of j. So it is don't care and 1. Similarly, we can complete the excitation table with 1 and 1, we get don't care and 0. So whatever type of flip-flop we decide upon, we have to be familiar with this excitation table and its truth table. So after knowing the excitation table of the flip-flop we have decided, we must be able to draw its state diagram. Now what is state diagram? We know that it is a counter, so it counts from one number to the other. Since it's a 2-bit, the counting sequence is 0, 0, 0, 1, 1, 0 and 1, 1. So it has 4 states or 4 modes. So in the state transition diagram, we draw the diagram of the sequencing of numbers. So it comes from 0, 1, 1, 0 is 2 in binary and 1, 1 is 3 equivalent in binary. So with respect to the state diagram, we must be able to write the state transition table. So in the state diagram, we know it is 2-bit and the 2 bits we represent as Q1 and Q2. So Q1 and Q2 in state S0 changes to 0 and 1 in the next state. So in the state transition table, we have a section for the current state, the next state, the value of the inputs for the two flip-flops. So for this case, we know we have considered two flip-flops. So the both flip-flops, J and K value, this is the J and K value for the first flip-flop and this is the J and K value for the second flip-flop. So for the current state, so we are starting with the first state. So in the first state, your outputs are 0 and 0. From 0 and 0, it is going to the next state, which is 0 and 1. Similarly, from 0 and 1, it is going to the state of 1 and 0. From 1 and 0, it is going to the state of 1 and 1. From 1 and 1, it goes back to the state of 0 and 0. So that is how you get the current state and the next state. So now I have marked with light green colors and dark green colors for the output and inputs of the first and second respectively. So if you look at the first flip-flop, we know J and K are the inputs and this is the previous output and this is the next value. So this is the previous value and this is the next value. So for this previous and next, what should be the excitation for our J and K? For that, we can refer to our excitation table and we know for 0, 0, the case is 0, don't care. So for 0, 0, we replace over here by 0, don't care. Similarly, for 0, 1, we write 1, don't care. For 1, 1, it is don't care 0. For 1, 0, it is don't care 1. So this we can easily write from the excitation table. So that is the case for the first flip-flop. The light green columns are corresponding to the first flip-flop. Now we have the darker green which corresponds to the second flip-flop, and here also we can do the same thing. Over here Q2, the previous value is 0 and the next value is 1. So we go back to our excitation table where previous is 0 and next is 1, our j is 1 and our k is don't care. So for previous 0 and next is 1, we have j1 and k2 as don't care. So like this we will be able to complete our state transition table. So once we obtain the state transition table for our counting sequence, we can go on to design our system. So to designing of the synchronous counter means we have to obtain an expression for our j and k in terms of the previous outputs, that is Q1 and Q2. So we have to obtain a relationship for both our flip-flops in terms of the previous outputs, that is Q1 and Q2. So there are two variables to decide upon the values of J1, K1, J2 and K2. So we make a 4-cell K-map with Q1 and Q2, and in Q1 and Q2 we have represent here 0, 1 and here 0, 1. So when Q1 and Q2 is 0, 0, when Q1 and Q2 is 0, 0, that is this cell, where Q1 is 0, Q2 is 0, for that value we have seen J1 is 0. So in that cell we can write J1 as 0. Next we can look when Q1 is 0 and Q2 is 1. So Q1 is 0, Q2 is 1. So the cell is this one. Over there the value of J1 is 1. Similarly, we will fill up all the cells of our K-map. So we have 0, 1, don't care, which says that we know how to obtain simplified expressions for K-map. We have seen that previously. So from this we can see that we can obtain a pairing for our 1 and this corresponds to J1 is equal to Q2. Similarly, we can obtain the K-map for K1, J2 and K2. For all the cases, the variables are Q1 and Q2. And after pairing the required ones, the expressions that we obtain for our designers, J1, K1 is equal to Q2 and J2, K2 is equal to 1. Since the whole cell is mapped, it is equal to 1. So we can now design our flip-flop. We have seen we need two flip-flops, two JK flip-flops. It is a synchronous counter, so we have to provide clock for both the counters. Next, according to the expression we obtained for the K-map, we have seen that J2, K2 is 1. So it is a high value. And J1, K1 is Q2. So the output of the previous flip-flop is taken as input for the next flip-flop. So now we have completed with the implementation of our synchronous counter for 2-bit counting sequence. Now we can see how we can draw the clock signal. So we have provided a clock. So we know a clock has got a rising edge, a level edge and a falling edge. So here we have seen our clocks are positive edge. Positive edge means the flip-flops are activated on the rising edge. So before we start the counting sequence, we will set both the outputs of our flip-flops to 0. Both the outputs are set to 0, that is Q1 and Q2 is 0. So at the rising edge, your flip-flop is activated. So the first flip-flop we have seen, it is given 1. 1 means your output will toggle. So your Q2 will toggle. Toggle means from 0 it will go to 1. And it remains the same till the next rising edge. Now what we have at the next rising edge, again since the inputs are high, it will toggle and becomes low. And that is maintained till the next rising edge, and then again it toggles to 1 and so on, it continues. While for Q1, we know the previous value of Q1 is 0 and Q2 was 0, which means that J1 and K1 at the start has value 0, 0. 0, 0 means it holds on to the previous value. So at the rising edge, it holds on to the previous value, which is 0, and the 0 is continued till the next rising edge. At this rising edge, the input to the flip-flop is the value of Q2. So what's the value of Q2? Q2 is 1. So when there is 1, what happens to your output? It toggles. And it toggles to 1, and that value is held till the next rising edge. At the next rising edge, we know that the input is Q2 and the Q2 is 0, which means that the flip-flop is 0, 0. Input is 0, 0. It holds on to the previous value. So it holds on to the previous value, which is 1, and it remains till the next rising edge, and so on. We can plot a waveform. So from this output, now how can we see the counting sequence? The counting sequence is such that is at the first instant you are counting 0, 0. At the next rising instant we have counted 0, 1. At the next clock rising instant it is 1, 0, which is 2. Next is 3, that is 1, 1. And at the fourth count it goes back to 0, 0. So our counting sequence is 0, 1, 2, 3 and again back to 0. Now we will see another example, that is a synchronous 3-bit up-down counter. So here again you will have to see the number of flip-flops required. Since it's 3-bit, we know we are counting from 0 to 7. And since we have to count from 0 to 7, the number of flip-flops required is 3. And for this example, I have considered a different flip-flop, T flip-flop, just to be aware of how we can do the designing of our counters with different types of flip-flops. So with T flip-flop, in T flip-flop, first we must be aware with the excitation table. So in the excitation table, we have seen, in the toggling circuit, we know that if the previous value is same as the next value, then it means that there is no toggling, that the input to T is 0. But if the next value is different from the previous, it has toggled, means our T value is 1. So likewise we can write, when the next value is same as previous, our T is 0. Our next value is 1, our previous was 1, so our T is 0. Similarly, when our next is 1 and our previous was 0, our input is 1. And when our next is 0 and our previous is 1, we have a toggling effect, so our T is 1. So with this in mind, we are going to design our transition table. So before doing the transition table, we have to draw the state transition diagram. So the question over here is was to design a 3-bit up and down counter. So the counter must count up and well as down. So in this counting sequence, you have 0, 1, 2, 3, 4, 5, 6, 7. So 3 bits means we know in binary, with 3 bits we can represent from 0 to 7. So the binary equivalent of 0 is 0, 0, 0. Equivalent of 1 is 0, 0, 1. So we need 3 bits to represent our number in binary. So up counting means it is 0 to 7. Down counting means you are counting in the reverse order, that is 0, 7, 6, 5, 4, 3, 2, 1. So in order to choose which mode of counting we are going to, we use 2 different signals. So one signal is when we have one control signal, when it is equal to 0, we are going in the up counting side, and when m is 1, we are going in the down counting way. So with that in mind, we can make the state transition table. So in the state transition table, it is very similar to the previous one. We have got 3 previous outputs and the 3 next outputs that is required, and corresponding values for our flip-flops. So now we have taken the case of up counting where our m is 0. So our first state is 0 our first state is 0. From 0, it goes to the next value of 1. Then, when we are at 1, our next value is 2. When we are at 2, our next value is 3. And 3, next is 4, 4 to 5, 5 to 6, 6 to 7, and 7, it goes back to the 0. So that is the counting sequence that we do. And in this counting sequence, now we can write the values for our flip-flops. So to obtain the value of TC, the input for the counter C, we have to look at the outputs QC and the next value of output QC star. So here we can see QC and QC star is remaining the same. So there is no toggling effect. So when there is no toggling effect, the input to T is 0. Next we can see QC is 0, QC star is 0. Again no toggling effect, so our T is 0. Similarly, we can take a case over here where you have QC is 0 and QC star is 1. So there is a toggling effect, so our TC is 1. So similarly we can write the values of TC, TB, TA. Vice versa, when we are going for the down counting, we can write the value of M as 1. And we know when it is at 0, the next value is 7. When it is at 1, 0, 0, 1, our next value is 0. In the down counting from 1, we are going to 0. When we are at 2, our down counting goes to 1. So like that we can write the current state and the next state. And we can write the values as mentioned before for our TC, TB, TA. Comparing QC and QC star, we can write for TC. Comparing QB and QB star, we can write for TB. Comparing QA and QA star, we can write for TA. So once the state transition table is completed, we can obtain the K-map for each case. So for K-map, the variables used are M, the control signal, QC, QB, QA, the outputs. So these are the variables used for designing our K-map. So for TC, for this value of TC, we can draw the K-map and we have M, QC, QB, QA, 0, 0, 0. That is the first cell. The value of TC is 0. For 0, 0, 0, 1, which is the second cell, the value of TC is 0. And so on, we can complete our K-map. For example, over here, if it is 1, 0, 0, 0. So 1, 0, 0, 0, we have to know that it is the 8th cell. At the 8th cell, the value of TC is 1. So vice versa, we can obtain the K-map for our corresponding state transition table. Once all the K-maps are obtained, we can obtain the relationship for our T flip-flops. So we have TC. So these are the K-maps we have obtained. From this K-map, we can see that all the values are 1. So our TA is equal to 1, which means for the TA flip-flop will give a high signal. In this K-map, we can see that TB is equal to M bar QA plus M QA bar. So we are all aware how to obtain the simplified expressions from K-map by grouping the ones to get an SOP expression. So over here the 4 ones are gathered and over here the 4 ones are grouped as a whole. And from this grouping, this is the expression we have obtained. So we have obtained M bar QA plus M QA bar. So you have QA and M bar QA, and you have the next one is M QA bar. Both are given to an O circuit, it is OR, and given as the input for TB. Similarly, we take the outputs of TB according to the expression and provide as input to TC. So this is how we do the logic designing of a synchronous counter. Thank you all.